Welcome everybody for this last session of this wonderful conference. The floor is to Mr. Dongping Zhong. Really curious what you had.
Hello, good morning. First of all, I really like to thank Jerry and also the organizing committee for inviting me to here to present our recent work on the water business. It's very interesting to listen why the topic is, and since I'm the physical chemist and also biophysicist, so here you may need to switch a gear to a very different topic. And here we really want to look at the water at a very local and a very detailed level and see what's the water property. As you know, water is very important. I'm sure you don't need me to elaborate too much. And then we try to find the water to believe maybe there's some living species in Mars. And also in cell, lots of the water channels and for water come in and come out to perform biological functions. And about like 2 decades ago, and with the supercomputer power, and the scientists can calculate the water behavior along the protein surface. And then I guess around the 2000, there are 2 very interesting papers, also very well known. And then Professor Pettit in the University of Houston, and he calculated the hydrogen sites along the myoglobin from the 398 hydrogen sites. He found out that most water stay there in biophysical distribution. And the one distribution is very fast, is around the femtosecond, which is 10 minus 15 seconds. And then another distribution is about 10 picosecond. And also, Martin Kapelos and with Greg also calculated this property. If we frozen the solvent, which mainly is water, and the protein will lost the activity. So that means the water is extremely important for biological activity and function. And meanwhile, as the ultra-fast spectroscopist, and the people say, well, we can detect the water motion dynamics. And back to 15 or 20 years ago, Stephen Box in Stanford tried to synthesize the artificial amino acid to probe the water. And meanwhile, at that time, in Caltech, I with the Ahmed, and we tried to use the intrinsic tryptophan. I'm sure everybody here know what is the tryptophan amino acid, and as the optical probe to study the water. So for past probably 15 or 20 years, we spent a significant effort to try to understand the water property along the protein surface. Here I showed one typical example. We took apomyoglobin, and then we mutate one at a time along the protein surface, roughly here 16 points with tryptophan, only one tryptophan once a time at the protein surface. We want to look at with the local perturbation of the optical probe, which is the tryptophan amino acid, and we want to see what's the dynamics of the water along the protein surface. The basic idea is following. In the ground state, the probe tryptophan is equivalent with the hydration water. Give the weak perturbation, which by electronic excitation, and then this system is in local non-equilibrium. And with time, the whole system will relax. During this time, if tryptophan can emit, we have the way to catch up the emission spectrum. The dynamics which tryptophan tells us is the labeling rearrangement, which is relaxation. In experiment, we use the fluorescence Stokes shift and to judge or to extract the information. And basically, in the lab, we use this very well-known or popular technique called the fluorescence upconversion with femtosecond resolution. We nearly can trace or follow all the water or labeling protein motion in real time. And basically, the idea is use nonlinear BBO crystal. We can tune the angle. We can selective the fluorescence wavelengths to mix with the gating pulse. We detect the upper converted signal, which is background free, and then we can get a wavelength specific and then dynamics. Here we show the final result. This is the time domain, and this is the emission domain. Basically, in the lab, we can construct the femtosecond resolved the fluorescence emission spectrum. And then this fluorescence emission spectrum is reflected the environment relaxation dynamics in time. With this, we can take the emission peak as the time, and we normalize by the maximum. Then we can get a correlation function. As the physicists, many people here, as we know the correlation function, then we can get many informations, lots of informations. And here I show the 16 points, the mutation on protein surface, one at a time, the dynamics. The blue line is the molten globule state, and the red line is the native states. You know, apomyoglobin is well studied, especially by Peter Wright in the squid. And then you can change the protein to molten globule state by changing pH equal 4 or 4.2. And the native is pH equal 6.3, something like that. You can see mostly water response is snow compared to molten globule states. Of course, you will see, of course, this is obvious because molten globule states, the protein still not formed the, three-dimension architecture, so water is not really formed beautiful hydration shell. So in this way, the water becomes faster. Among the 16 points, only 1 point, the molten globule state of water is snow than the native states. Actually, for this point, by molten globule states, the origin is the helix turning point, the terminal point become the helix. So that's why it becomes snow. By this measurement, we get two very important parameters, physical observers. One is the energy, the relaxation energy. How much energy relaxed by local environment and by this stock shift. Another is the time. Let's look at this energy. And then basically, this is the emission peak. And the emission peak, tryptophan fluorescence emission peak, tells you where the tryptophan is. If the tryptophan is fully exposed to the water, and then emission peak will be 350, very fully exposed. When tryptophan is fully buried into the surface, then the emission peak will be very blue. It's around 320 to 330. So from here, you can tell the energy relaxation for each mutant is a monotonic increase. In a sense, you can see this looks like a water response. And if you can look at it carefully, all the correlation function, like early days simulated by computer, is by physical distribution. And we can divide this two by physical distribution. For the first one, it still is monotonic. In simple language, this dynamics is reflect all the water response, which roughly around the 10 angstrom the water around the optical probe. And then the snow motion is very interesting. The energy relaxation looks like this kind of shape. When the tryptophan is fully exposed to the water, then the energy more or less like a constant. And here we attribute this energy relaxation from the inner shell water, inner layer of the water among this hydration shell. Basically, if the tryptophan expose the surface more and more, you detect all this 10 angstrom first or second shell of water. then your basically energy will not change too much. Okay, this is a energy point of view. You can tell roughly what's going on. And of course, the second most important is the time. You can quickly look at the molten globule states is much faster than the native states. This makes sense, right? Because molten globule states, only the core is formed. So the hydration shell is not fully already formed. It's networking. You can see the dynamics observed is very well correlated with the protein local structure and the chemical identity. We can beautifully assign all these dynamics with the protein property, okay? Both for the fast time scale and also for this slow time scale. Extremely for slow time scale and relate to the protein local rigidity. For example, for loop, the water will move faster. For the alpha helix, water will move slow, near slow. And you can also see the tau 1, tau 2, this time the correlation. For molten globule state, is pretty well correlate, especially a few points which you can understand with structure. But for the native states, it's a wider distribution because this time scale is really correlate the protein property, both structurally, geometry, and the chemical identity. So also, we go to measure the protein side chain motion, which here is the tryptophan side chain motion. And we find out all the side chain motion is longer than we observe the so-called water hydration motion in this region, which I back to this point very importantly later. And here we quickly summarize. Originally, we observed the 2-time scale for water arrangement around the protein surface. The tau 1, a few picosecond, basically is local relaxation. Basically here, it's a lot involving larger translation motion. It's the liberation or hindered rotation. And then the second one, the long time is 10 picosecond, involve water rearrangement, this lateral walking, and upon on this new dipole excitation, back to the new equilibrium. Of course, meanwhile, the water will exchange with the bulk water, and we can simply in cartoon fashion, we can draw the water, hydration water is in non-equilibrium, goes to the equilibrium, and the protein is help the fluctuation, is coupled. Without the protein, water couldn't relax, vice versa. And here, this water also do exchange with the outside bulk water. So it's very complex, it's convoluted to at least two different motions. So after we publish this, there's a big debate in the literature, especially with MD simulation. And people don't believe the water can make a 10th picosecond. I'm sure you know, in 1980s, 1990s, with ultra-fast studies, people pretty much understand the water dynamics in this kind of free water dynamics here. I'm sure you know. The hydrogen bonding and the arrangement in the free water is around 1 picosecond, which is 10 minus 12 picosecond. So people had to believe on the protein surface how water can snow like a 10 picosecond, even 100 picosecond. Even we tell the people, say, this is really coupled motion with the protein side chain or backbone. So here I show you one example. We did the MD simulation. So first the diagram is we use linear response, use a long range trajectory. We calculate the correlation function. Here you can see the total energy relaxation is fluctuation is really dominated by water. Actually, protein contribute a very ultra fast component here. And here we use non-equilibrium trajectory average on the excited states of the tryptophan. And this is the average 600 trajectory average. And you can see this is also water dominant. However, I have to say, if you go to current software, even Charm, the Glomax, all these things, Amber, and most of the time, you go to simulation, you still find out the majority response for this lung equilibrium is from the protein, which is the debate in the literature even today. So if you back to look at the NMR studies for water, and the people do observe that this 10th picosecond dynamics in the solution, even though NMR resolution is not as great as like optical, but they do observe this so-called snow water motion in biological system. And similarly, by neutron scattering, here the neutron scattering to detect the fluctuations, and then they can detect the protein alone and the water alone, the hydration water alone. You can see here the hydration water is fluctuation is much larger than protein fluctuation. So in a sense, I always thinking if two things coupling motion, you want to determine that is really mutually coupling motion, or is A driving B or B driving A, like this. The only thing you can do is two ways. One is you look at the time, which is move faster. If you can measure independently the optical, the object A and the object B, if the similar, very similar, then you can think it is a coupled motion. If one is move extremely faster, maybe the fast one, is push the slower motion. Or you can look at the amplitude. If one is move very large amplitude, another is move a tiny, then you will think about the large amplitude motion object will driven the slow amplitude motion. And here also have evidence the water is driven protein fluctuation. And then, of course, recently people also use NMR to do temperature dependence, look at the hierarchy of the side chain, water, protein backbone, all these kind of motions. I'm sure there's also X-ray absorption, terahertz, and the MD simulation. All people try to understand the first layer, second layer, third layer, how water behavior around the protein surface. I'm sure many people here know this work by Hans, and Hans proposed on the serious paper to say the water is dominant to drive the protein fluctuation. And he used this polymer language, say is alpha relaxation by the water fluctuation to make the conformation fluctuation, and then in the hydration surface, and then the water is driven protein fluctuation by called the beta relaxation. And of course, and the physicists like this, but the biologists don't believe it. And then, so recently we say, well, let's really do good job. We take this giant protein is a DPO4 polymerase. This protein low tryptophan, which is good for us. We can do side direct mutation one by one. So this protein has 4 big domains, and then we put each domain have 3 or 2 points. So total 11 points, one at a time. We carefully to study this system with temperature dependence. So we can get all this spectrum, time resolved fluorescence, and we also can measure each side chain tryptophan, the dynamics in time and with temperature. We get all this. You can see here for room temperature, similar result we observe for apomicrobic. And this is extremely important data. Probably is the most informative of my talk. You can see here first, we measure the protein side chain tryptophan motion very carefully precise. We observe actually tryptophan side chain also has 2 time scales. And then the first time scale, the tryptophan wobbling, we call the T2W, with the faster the water motion has a beautifully linear correlation. The line goes through the 0. And for all the mutation, exact same, that goes through the 0. And similarly, the tryptophan and also have a long time the wobbling. And then also we plot out this tryptophan time with the water long time, the water 10 picosecond together with the temperature, each temperature from the 1 degree to let's say 60 degree or 80 degree. Where temperature is a shorter range, but you can see the time can change by a factor maybe 4 or 3. And then you can see also beautiful linear for each mutant. If you know roughly, think about this, the relaxation is the rate process. You can see this both process actually share the same barrier, even may have different prefactor. In a simple language, this two fluctuation, water with protein side chain, actually from the one origin. So actually either is from the coupling motion, is the same thing, or is one driven one, and actually is the same thing by this the motion. And then we can plot out this temperature dependence, even we can figure out all the barriers, and also we can figure out the prefactor. Interesting enough, for some water extrude to the water surface more, we also can detect the third layer, fourth layer. The third layer, fourth layer, the water prefactor here, barrier, which I show you later again, the barrier exactly looks like a free water barrier, which I show you free water barrier later on. And then the prefactor, which you can think about, assume the barrier equals 0, what's the fastest motion of this free water? This exact is 20 to 30 femtosecond. If this is the exact predicted by theory, the free water can fast motion in 20 femtosecond, which is exactly we measure here. So we can get all the information about this barrier motion and then prefactor, which probably involve the entropy. You know, all the information here, we can roughly construct this kind of diagram. Before I show you the details here, I have to say, if this water and the protein is the same, and also we find out all this curve is above this equal, that means the protein fluctuation side chain always slower than the water fluctuation. We take the ratio here is among the 1 to 5. Basically, it could be water fluctuation 5 times, and the side chain, they are slowly fluctuating. In a sense, looks like water is driven for side chain fluctuation on the picosecond time scale, So if this is true, we can draw this simple diagram. So basically, the water will driven the fluctuation first, and then driven the protein fluctuation side chain, and back and forth to the equilibrium. And this is the truly empty simulation. We can trace each water on the protein surface and see how they are fluctuating with the time. And of course, the one thing people criticize, say, we just don't believe, because the protein side chain should make some contribution. You all attribute this motion to the water. So here, we took another protein, staphylococcus. We fixed this probe point. Around this probe point, have the 3 charge wrapped around this protein tryptophan surface. And what we did is we do 1 by 1 mutation, 2 by 2 mutation, 3 by 3 mutation, and finally we muted all the charges. This site become complete hydrophobic site, and the protein is perfect in the contact. Is the protein structure is perfect, okay? So in this way, you can see, very interesting, without doing time resolved studies, the emission spectrum already show you no change or change red. It's not a change blue. If we use a computer to simulation, use MD, use the best force field, water and protein force field, you will find out the spectrum will shift to blue because the charge you mutate out. Because you calculate 80% stock shift are from the charges, which is not true from this case. And with all this, we can do all the time resolved study, we can do temperature study, and then exactly like before, as I show you, all this pattern is perfect, beautifully show this. So in this way, we find out the conclusion from the DPO4 is a hold. Is similarly, is water is driven protein on the faster time scale. I'm not to say this way extended to the nanosecond, microsecond. At least on the picosecond time scale, it looks like water fluctuation is driven coupled and driven the protein fluctuation and back and forth. So finally, we took one protein back to apomyoglobin because my apomyoglobin is interesting. They are very rich of all the surface. So we say, let's take 5 complete different chemical property and geometry property, and we look at what's going on. Similarly, we did the temperature studies, and then I just show you final result. Exact the same result as staph nucleus, exact the same result as the DPO4. However, there are some difference. From the 2-time scale with temperature, we can plot out these berries. This berry is very small, around 10 to 15 kilojoule per mole, which is equivalent in roughly 2 hydrogen bond, 1 to 1 to 2, 1, roughly 1.5 hydrogen bond on the average. It's a very weak small berry. And then for this one, if we put a probe on the well surface, we can detect the also free water, like 4th snail, 5th snail, and this water exactly is free water. This is a tryptophan in back water, and then there are 2 motions is well long, and we do temperature dependence. The first berry is around 5 to 6 kilojoule, and this is 7 kilojoule per mole. This is free water for the 2 dynamics. And then if this on protein surface, the tryptophan, we can detect basically 2 dynamics on the inner layer, and 1 is outside free water. You can see here for DPO4, this berry is very close to the free water berry, but the second berry is high. For apomyoglobin, this is significantly larger. But if you put the probe inside the berry, the protein, you only detect the first layer, at the most the second layer water. You can see this is truly hydration layer, the arrangement of the berry. You can see for DPO4, staph nucleus, apomyoglobin, the berry is different. However, for each protein, you put 10 mutants or 20 mutants, the berry is the same, even though the dynamics is very different. So in a sense, this berry looks like a global property. However, the dynamics time is in fact a local property. This is very interesting. Right now, we try to find out, we have more samples, more proteins. We want to figure out that this berry, what this berry tells us, and what it relates to. Is it related to protein the size, related to the protein rigidity, related to protein surface area, etc. And then we try to understand this. From all these 3 systems we did, right now we get a feeling, yes, on the fast time scale fluctuation is really the water is driven the protein fluctuation. And in this region, probably is inaccessible, because here in this region is a protein driven first, and then to drag the water fluctuation. And then here, this region is water is driven the protein fluctuation. So in a sense, hence Flanfeld's idea the hydration water follow the beta relaxation looks right. At least for this process with this protein result is a strong support of his idea. Okay, so finally, quickly, I try to acknowledge most students did work. Luckily, early days we have 2 postdocs involving the water, and then we have 6 students for past 10 years and involve water. And initially, I started water at Caltech with Ahmed, and then later on I moved to Ohio State and collaborate with Shun Singer, is a theoretician. He is an expert on ice for many years, and we supported by NS and NIH. I stop here. Okay. Yeah.
What a powerhouse presentation.
I speak faster, you know.
Yes, and you're very driven and enthusiastic. On behalf of everybody, thank you very much.
Okay, thank
and
you.
I wonder if there are, yes, an extra applause. Yes, I'm not surprised that you have a question. Yes.
I echo that. Thank you very much for a wonderful presentation. How much could the lessons that you have learnt teach us about the relationship between water and DNA, and whether or not, for example, there is a DNA-specific relationship between the water and the DNA structure?
Okay, that's a good question. Actually, I didn't show here. At the beginning, I was involved in hydration at Caltech with Ahmed. So I'm sure you ask this question, you know the literature, what's going on right now. So DNA hydration initially investigated by, I would say, at the molecule level, at this time scale level, by one is Ahmed, at Caltech in 1990, around 1993, the time I'm leaving Caltech. And another is by Mark in the South Carolina State University. DNA relaxation, of course, we couldn't do like an ensemble average, we always do site specific, as you said, if we put a probe to probe the major groove or put the minor groove, all kind of dynamics. And then, if I remember right, the DNA, if we give perturbation, the DNA relaxation, the DNA and the water relaxation from the picosecond, same as here, more or less, the time scale, until to probably until to 10th nanosecond, could be longer. And then this, induced a huge fighting or discussion in the literature, especially about MD simulation. I'm sure you know that Stephen Cosella in the Notre Dame, he pushed this very hard. Beneath all the this motion is by this salt, because DNA has a lot of salt with the phosphate interaction, and also by the DNA fluctuation. The only issue bothered me, and then including recent Casey Hines did a lot of the simulation. The only thing bothered me, this MD simulation somehow to treat this interface, the water and the biological molecule could be questionable. So my point is how reliable this MD simulation can give some trend, but I couldn't tell you exact this is water motion. Of course, MD can tell you in reality may not be true. That's my opinion. So right now, they can do MD simulation, no problem. They can get the water dynamics signature with DNA, especially bDNA, and then geometry. In the minor groove, water will trap there, order there, and the major groove, water is a little bit mobile, and all this kind of information. But experimentally, interpretation still is very different from the MD simulation, at this stage,
Any more questions?
Yeah, I'm David Jonsson, Sweden, private consultant. I have a question regarding, you say that motion is driven from the protein to the water. Are you then also saying that the energy is going from the protein to the water?
The conclusion is water to protein.
From water to protein?
No, the conclusion, sorry, maybe either I speak too fast. Our conclusion at a picosecond time scale is the water, hydration water, is driven the side chain fluctuation. The reason is the water time is much faster than the side chain wobbling motion there. Of course, this is the wobbling we believe right now is the water fluctuation push the side chain fluctuation on the surface, even maybe backbone, on the picosecond time scale. Yeah, by the temperature studies, both dynamics exact the same. Either is a complete coupling, nobody is chicken and egg, number one. Number two, or is water driven, because from the data, the water motion, according to weight measurement, is either equal to the tryptophan side chain motion either equal to water motion or either slow by factor by 6 times or 1 to 6 times slower. So in this way, we believe if we have A, B, they are coupled. If this is a much faster motion, this is just slow motion, in a common sense, this probably can driven this. That's the conclusion. That's the original idea was proposed by Hans Flamfeld, this beta relaxation on the in the hydration shell.
But isn't the energy exchange, if you have an enzyme with a lot of energy production, isn't that motion then driving water? How could it be else opposite?
You mean the energy, which energy?
Yeah, the energy of the motion has to come from somewhere. Where is the source? Where is the flow of energy here?
Where's the flow of the energy?
Or is it the equilibrium perfect?
Yeah, it's we do non-equilibrium. If linear response hold, roughly it's the same as we try to say this is the equilibrium. So my point is, when the equilibrium fluctuation, the water is fluctuating much faster than protein side chain. So that's why the water fluctuation is driven protein side chain motion. That's it. That's the only way our conclusion. Yeah, yeah. It is a thermal fluctuation. It's this result is implied this local thermal equilibrium fluctuation. Yeah, dynamics.
I wonder whether your data are consistent with the possibility, as has been discussed here a little bit at the meeting, of a transition in the water between an easy water surrounding the protein and bulk water. And that transition would produce rapid motion in the water, which would then be conferred to the protein. Are you able to say a few words about whether that's a possibility or not based on your data? Maybe not. Okay.
It could be, we need more experiment. Yeah, we can design more experiment. You go to test, yeah. Go to systematically test, yeah. Yeah, we can talk, each other, and then we can really design some test to easy water, say, can we really design nice experiment to say, yeah. Yeah, that would be good, a very good idea. Yeah, very good
Thank
idea.
you.